Okay, so we'll continue on with the 5 areas of electron density. Remember, we said 2 areas, the electron geometry is linear. 3 areas, electron geometry is trigonoplanar. 4 areas, the electron geometry is tetrahedral. 5 areas, the electron geometry is trigonal bipyramidal. And we said that the molecular geometry is exactly the same as the electron geometry if and only if there are no lone pairs around the central atom. If there are lone pairs around the central atom, then the molecular geometry is going to be different. So in the last video, we ended with the seesaw, where you have one lone pair around the central atom when you have a trigonal bipyramidal electron arrangement. So that becomes a seesaw molecular geometry. And I said that anytime you have a trigonal bipyramidal arrangement, electron arrangement or electron geometry, if you're going to have lone pairs, you always put them in the equator, in the equatorial position, around the equator, not in the axial position. Okay, so the next molecule is chlorine trifluoride. And I crunched the numbers already. Go ahead and practice doing that. S is equal to n minus a. You will see that you've got 5 electron dense areas. 1, 2, 3, 4, 5, with 2 lone pairs around the central atom. Don't know if you could see the lone pairs well. Hopefully, make them a little brighter here. Okay, so hopefully you see that. Okay, so that's 5 electron dense areas. The electron geometry or electronic geometry is trigonal bipyramidal, because 5 is always trigonal bipyramidal. Okay, so what would the molecular geometry be? Okay, let's take a look here. All right, so this is the typical trigonal bipyramidal, but now we've got 2 lone pairs. So this is a lone pair and a lone pair. Keeping the axial position, this is the equatorial. So there, this is 1. Go like this. If I flip it this way, what does it look like? Doesn't it look like the letter T? So they actually call this T shape. Okay, what are the angles for this? Now we got rid of the 120 because we don't have the 3 in the equator or the 2 in the equator. Now we just have a 90 and a 180. So the angles are 90 and 180. Okay? And what about polarity? Well, it's not completely symmetrical. You've got these 2 lone pairs, but these 2 lone pairs are not canceling each other out because you got the fluorine over here. So this would be considered polar. Okay, so that's that one. Practice the S is equal to n minus a for this one. The more you practice, the easier it's going to be, and the faster you'll be on an exam, okay? All right, so this is another one, xenon difluoride. Remember how I told you guys in the videos in chapter 9 that xenon can be a central atom because it uses the D zone, and even though its octet is full with S and P, it will use the D zone, and it can actually do some bonding. All right, crunching the numbers, you're going to see that you have 5 electron dense areas. Single bond, and then you have 3 lone pairs around the central atom. Okay, make it a little darker so you guys can see them. 3 lone pairs. Okay, so the electron geometry or electronic geometry, because there are 5, 1, 2, 3, 4, 5, it's trigonal bipyramidal. Trigonal bipyramidal. Squish it in here. Molecular geometry obviously is going to be different. Why is it going to be different? Because you got all these lone pairs. All right, this one's going to be pretty obvious. I'm going to take this guy away. So I have 5 areas, 1, 2, and then the 3 lone pairs around the central atom. But when you do molecular geometry, you're just looking at the peripheral atoms. How are they arranged? They're arranged in a line. So the molecular geometry here is linear. Okay? Bond angle is easy. It's got to be 180. Now, here's where it gets tricky. Is it polar or non-polar? Well, this and this symmetrical cancel each other out. These three lone pairs, the way they're arranged perfectly around the circle as three vectors, they all cancel each other out. So because they divide the circle equally, they cancel it. So they cancel, these guys cancel, so this would be considered non-polar. So this is non-polar. Okay, obviously, if instead of a fluorine, I had a chlorine here and a fluorine here, if these two guys were different, then obviously it would be polar. But if they're identical, and then the three lone pairs cancel each other out, this would be considered non-polar. Okay, so we're ready to move on to the 6 areas of electron density now. We have a couple of those to deal with, and then we'll be all done with all the different molecules that I want to make sure you get introduced to. Okay, so what's the next one? The next one is sulfur hexafluoride. Remember we did that in chapter 9, sulfur hexafluoride. Now, the way we're going to draw the ones that have 6 areas of electron density, you have 2 in the axial position and then 4 in the equatorial position. So this is going to go in, this is going to come out, wedge. Here's a wedge coming out. I'm not an artist. This is going to go in. So I'm trying to make it look as 3D as possible. Like I said, definitely not an artist, guys. Okay, so this is my, oops, too many lone pairs. This is my sulfur hexafluoride. Let me show you what it looks like. Here we go. Here it is. Sulfur hexafluoride. So these are my 2 axial ones, and these are my 4 equatorial ones. There we go. These are the 2 coming out. These are the 2 going in. This is what it looks like. Okay? So what is the electron arrangement or electronic geometry? Anytime you have 6 areas, and here we have 6 areas, 1, 2, 3, 4, 5, 6, it's called octahedral. Octahedral. So this is 6 areas is octahedral electronic geometry. Okay, the molecular geometry for this would be the same. Why? Because there are no lone pairs. So this is also octahedral. Okay, let's take a look at the bond angles. What would the bond angles be? Well, you can see the 90. And then if you look at the equator, they are all 90 also. And then the big long ones between this, and these across, those would be 180. So you don't have any 120s here. You have 90 and 180. So 90 and 180. Okay. Polar or non-polar. These 2 guys cancel each other out. These 2 guys cancel each other out. These 2, I mean, all identical peripheral atoms. So this one specifically is non-polar. If one of the fluorines was replaced with something else, then obviously it would be polar. Okay? All right, so that's that. Let's do another one, but now we're going to throw some lone pairs on the central atom. So the molecular geometry is going to change, because remember, the minute you have a lone pair on the central atom, the molecular geometry is not going to be exactly the same as the electron geometry. Unlike with trigonal bipyramidal, here when we put electron pairs around the central atom in octahedral, you put them in the axial position, not the equatorial. So you put them up, down, rather than around the equator. So the next one we're going to do is IF5. Iodine, Penta, Fluoride. Okay, let's go ahead and crunch the numbers together just for practice. S is equal to N minus A. All right, the needed, remember, is 8. Everybody is 8. So we've got 8 times 6 is 48. The available is 7 because these are all halogens. 7 times 6 is 42. So 48 minus 42 is 6. Okay. 6 means you have 3 bonds. Obviously, that's wrong. What do we have to change it to? We have to change it to 10. Why do we change it to 10? Because we can see that we've got 5 peripheral atoms. So let's go ahead and do this. So we're going to put an iodine. That's in the middle. Remember, fluorine is never in the middle. Okay, and we're going to have a lone pair, but let me just, okay, let's pretend I don't know what it's going to look like. So let's just go ahead and do it. Draw it like a flower, even though you're not supposed to, just for now. Okay, so I put all 5. All right, how many electrons do I have to distribute? 42 minus 10 is 32. So go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Where do I put 31, 32? 31, 32. Boom. Okay? 6 areas of electron density. So the way this is going to be drawn, this is not bad actually. You put the electron pairs in an octahedral in the axial position. So technically, to draw this, actually, you know what? I'm going to leave it as is. I'm just going to, instead of these bonds, I'm going to make them sort of poke out so that I can show that they're poking out. And then these guys are going to be dotted lines going in. So it's not really a flower. Okay, there we go. So, electron geometry. We know that since we have 1, 2, 3, 4, 5, 6 areas, because you've got to count the lone pair, 6 areas, it's going to be octahedral. Okay, but what would the molecular geometry be? We know that the molecular geometry has to be different because we have this lone pair. So let's take a look at it. I'm going to remove this guy from the bottom. So I have this lone pair here. What does it look like? Well, it sort of looks like a pyramid again, but instead of having a triangle base, it's got a square base. So it's called square pyramidal. Okay, instead of trigonal pyramidal, it is square pyramidal. Square. Square pyramidal. Okay, what about the bond angles? What would the bond angles be? Well, I can still see the 90s, and I can still see 180. So it's 90 and 180. And because we have this lone pair here now, doesn't cancel this over here. So now it's not perfectly symmetrical. So this one specifically is polar. Okay? Good. And then the last one we've got is a Xenon Tetra Fluoride. So again, it's going to have, this one's going to have 2 lone pairs instead of just 1 lone pair. And it's going to look like this. So Xenon, and remember, whenever we have an octahedral, we're going to put the lone pairs on the central atom. I already know what this is looking like. So this is Xenon tetrafluoride, but you can crunch the numbers and prove it to yourself that this is what it's going to look like. And then put all the lone pairs around. Again, please practice crunching those numbers, guys. All right, the important thing is that you have a lone pair down here in the axial position and the lone pair up here in the axial position, okay? So right now, this is what it's going to look like. Lone pair here, lone pair here. And then all the equatorial ones are still there. All right, so what is the electron geometry? Well, there are 6 areas, 1, 2, 3, 4, 5, 6. So it is octahedral. But like we've been saying over and over again, the molecular geometry is not octahedral because there are lone pairs. If there were no lone pairs and there were actual atoms, yep, it would be the exact same thing. Okay, so we've got this. What is this called now? Well, it looks like a square, but it's not a pyramid anymore. It's on a plane, so it's called square planar. Okay, so this is called square planar. That would be the molecular geometry for this. All right, bond angles. Let's take a look at the bond angles. I see a 90. See the 90? See the 180? Yep. So we've got 90 and 180 still. And then now let's focus on polarity. And this is where it's really cool. You got this lone pair exactly opposite this lone pair. This is the only time this actually happens. The lone pairs are exactly opposite each other, so they cancel each other out, perfectly symmetrical. These guys are exactly opposite each other. Everybody's perfectly symmetrical, so this is nonpolar. So it only happens in the square planar scenario where the lone pairs are exactly opposite each other and can cancel each other out. Okay, we are all done with all the molecules. Next video, we will talk about something else.